This will be the lecture for Module 9, and it will cover a little bit of Chapter 11 and a little bit of Chapter 12. This is all going to be about our study of fluids. So hopefully you've already completed the reading assignment and have a basic understanding of what that means. One of the first important properties we can use to help us in our study of fluids is density. And remember, density is represented by this symbol. It looks like a P. It is the Greek letter rho right here. And to find density, we're just going to use mass divided by volume. So let's try out a problem. A reservoir has a surface area of 50 square kilometers and an average depth of 40 meters. What mass of water is held behind the dam? And I gave you a picture of it just so you could see a photo of a really large reservoir. So here, since our ultimate goal is to figure out the mass of water, and I have information about the surface area and the depth, which could probably help me find the volume, I know that I can use something with the density, especially since we know water is the fluid held in this reservoir or behind the dam. If you look in your book in table 11.1, you can actually find the density of water, and it's a nice, easy number to remember. It's 1. And the unit is 1 times 10 to the third kilogram per meter cubed. Well, since we have kilogram per meter cubed, we're going to need everything in kilograms and cubic meters. And I only see one issue with that as of right now. So let's go ahead and rearrange our equation, this, so that it says mass equals, which means we're going to take the V over there, and we get mass equals V times density. Well, we have density, we do not have volume. But remember, the volume of something that has a surface area and a depth would ultimately just be that area times the depth, or length times width times height. They've just done a little bit of that for you already with the 50 cubic meters. So if we have something and we could estimate this to be sort of the size of like a rectangular prism, then our volume is just going to be the area multiplied by the height. So let's get these in the same units. 50 kilometers. Let's take that to meters. And this is squared, so that I'm going to have 1 kilometer. And we know that there are 1,000 meters in a kilometer, but I have to square this as well, since my kilometer is squared. And you should get approximately 5.0 times 10 to the 7th, and that'll be square meters. So then volume is 5.0 times 10 to the 7th meters squared, multiplied by the height, which is 40. And that value is about 2.0 times 10 to the 9th meters cubed. So let's just go plug in our information. We have mass equals 1 times 10 to the third. It's kilogram per meter cubed. And we have our volume, which is 2.0 times 10 to the 9th meters cubed. All we need to do is multiply here, And you should get a really large value here, which makes sense. Dams hold a lot of water. You end up with something to the magnitude, or about 2 to the magnitude of 10 to the 12th kilograms. So it's pretty massive. And there's your answer. Another really important property of fluids is pressure, and pressure can be found by dividing the force by the area over which that force is acting. So let's look at another problem. An astronaut is walking outside the International Space Station where the atmospheric pressure is essentially 0. The pressure gauge on her air tank reads 6.90 times 10 to the 6th pascals. What force does the air inside the tank exert on the flat end of the cylindrical tank, which is a disc 0.150 meters in diameter? Now, if you've completed that reading, you'll know that Pascal is a unit for pressure, which means they've given you the pressure, they gave you a diameter, and it wants to know the force. So let's write pressure equals force over area here. We're looking for the force, we have the pressure, and we know the diameter, and then we also know that the tank is cylindrical. So let's use that information to help us find an area. Well, if we're thinking about the flat end of a cylindrical tank, that would be a circular shape. So then the area of a circle, here will be pi r squared. We already have our value for diameter, but we need radius, so we're just going to cut this in half. We'll find that that's 0.075 meters. So then it's pi times 0.075 squared. And that shows that the area of the circle is around, 0.01767. 0.01767, and that's meters squared. So let's just rearrange our formula now. We have P equals F over A. We want force by itself, so we're going to do something similar. Now we have force equals area times pressure. Area is 0.01767 meters squared. And the pressure is given to us in the problem. So let's just plug that in. 6.90 times 10 to the 6th pascals. And we'll find that force then, when we multiply these values together, is 1.22 times 10 to the 5th newtons. So we still have our same unit for force, which is newtons. We will now look at a slightly different problem. So in the first example, we calculated the mass of water that's in a large reservoir. Now we're going to consider the pressure and the force acting on the dam that's retaining that water or holding the water back. The dam is 500 meters wide and the water is 80 meters deep at the dam. So what is the average pressure on the dam due to the water? And then calculate the force exerted against the dam and compare it with the weight of water in the dam. All right, let's start with part A. For part A, and if you look at your formula sheet for chapters 11 and 12, you should see this. We're actually going to need a slightly different formula. And this time we're going to be using pressure equals height times density times G, or gravity. Well, we need this because we have a significant depth of water and pressure will change with depth. You've likely experienced this if you've just swam to the bottom part of a swimming pool. You'll feel the changes in your ears, or if you've flown on an airplane. So we have this information. It tells us the depth of the water, which was 80 meters. Let's see. It is water, so we already know the density. We wrote that on the last slide, or the one of the previous problems, and that was kilograms per meter cubed. And we know the value for gravity. So this one's really simple. We just had to plug in our information and solve. And you'll get about 7.84 times 10 to the fifth, and that's going to be pascals. So that's what pressure is. Okay, now we can take a look at part B, which I'll do in a different color. So this is the average pressure on the dam due to the water. For this next one, it wants to know the force exerted against the dam. All right, well, that's where we're going to have to look at this formula again, P equals F over A. And since they want the force, let's rearrange this. We're going to get F equals P times A. We just calculated the pressure, so we can plug that in. 7.84 times 10 to the fifth pascals. And now we're going to need our area. Well, this one's not too bad either. We are given two very valuable pieces of information here. We are just talking about this section of the dam. So it forms a rectangle, not a rectangular prism. So it's just this area that the water's in contact with, which would be length. Oh. Whichever way you want to look at this. If you want to do length here and width here. Oh, no. We're going to stick with how they've chosen to do it, which is length here and width here, or height. Doesn't matter. This is area. So then to find area, we're going to have 500 meters multiplied by 80 meters. And we will find that 500 times 80 is, let me do this. $500 times 80 is 40,000. That's meters squared, so let's plug this in. And then we'll find that the force is 1.57 times 10 to the 10th. And that's newtons. Finally, compare this with the weight of water in the dam, and we calculated that in a previous problem, so let's go ahead and compare. If we want to compare, I'll go back and use, how about this color? So we're going to compare it to the weight of water in the dam, which was, I'll write this first, 1.57 times 10 to the 10th newtons. So if we're comparing it, let's go back and find that value. It was 2 times 10 to the 12th, correct? But it said the weight of the water, the weight. So we got 2 times 10 to the 12th. Let me go back and write this down. So that's going to be 9.8 times 2. Yes. So since they want the weight, don't forget to multiply mass and gravity. And you'll get 1.96 times 10 to the 13th. And then we can also have weight in newtons. That's not an issue. So when you compare those, you will find that the force as compared to the mass of the water, I'm just going to go write it up here, is about 0.0008. And when we turn this into a percent, that'll be 0.0001. 0.008% of, oh wait, I think I did one too many. Yes, we need to get rid of 10. There. Percent of the force from the water as compared to the actual weight of the water. It's just a very small fraction of the force from this water. So that's going to be the first part. There is more, but I'm going to go ahead and split this into 2 videos.